In this video, we're going to talk about the Faraday cage and its working. Faraday cage works to exclude an external electric field and create an internal electric field of zero through the principle of electromagnetic shielding. It does so by exploiting the behavior of conductive materials in the presence of electromagnetic field. So, how does it work? So, Faraday cage is typically constructed using conductive material like copper or aluminum or other material. These materials have a large number of free electrons that are uh, able to move easily within the conductor. So this, let's suppose this is our cage. Like all material in the universe, it is electrically neutral. So electric charge are equally distributed in the conductor. When an external field approaches the surface of the Faraday cage, it exerts. So this is the external electric field. It exerts a force on free electrons within the conductor. The electric field causes the electron to move and redistribute themselves across the surface of the cage. So what does that mean, redistribute? Redistribute means that uh, suppose this side of cage is electrically negative charge and this side is positively charged. What will happen? The movement of electrons in response to external field result in accumulation of charges on the surface. So this is accumulation. This accumulation of charges create an opposing. So opposing electric field that uh, cancel out the external field within the cage. The redistribution of charges on the surface of the cage effectively neutralize electric field inside the enclosure. As a result, the net field inside the Faraday cage becomes zero. Since the internal field is zero, any object, let's suppose PCB was placed inside this Faraday cage. So it is not affected by the external field. The cage essentially acts as protective shield, isolating its interior from external electromagnetic interference. So this was the basic principle of Faraday cage. Now question arises: what will happen uh, if external field is alternating? So in that case, if the external field is allowed to alternate, meaning its charge or uh, its direction or magnitude over time, as in the case of alternating current or AC, the Faraday cage will still provide a certain level of shielding, but its effectiveness in excluding the external field will be reduced as compared to shielding against static or low frequency field. So in this case, first case, we assume that external field is constant, it's not changing, and it's low frequency. So in that case, it's easily the charges are redistributing them. It's easily. So here it will be negative, and here it is a positive. So what will happen if we alternate first? Let's suppose this is the alternating electric field. The lines are reducing, then again increasing. So this electric field, external electric field is alternating, then the shielding effectiveness Faraday cage typically decreases as the frequency of alternating field increases. Why does it happen? Like Why exactly? The induced current on the charge may not have enough time to redistribute and cancel out electric field completely during each cycle. So in the first case, we thought that the field was constant, so it was easily canceling the external field. So this whole side was negatively charged, and this side was positively charged. When it's alternating, then what will happen? First, it will be positive, negative, and then it will be positive. Then this side will be positive and then negative. And then it will continues to positive and negative, positive, negative. So if the frequency increases with the time, then uh, the result can, like, it charges can't keep up with that. Like, uh, yeah, certainly this will be here will be negative, then it will again it will be positive, again there will be negative. So with a change in frequency, if frequency increases, then uh, the external field will overcome the opposing field and will penetrate inside the cage. While Faraday cage may still provide some attenuation and protection against low frequencies, alternate fields, it may not as effective at higher frequencies, especially at in the radio frequency or microwave ranges. Now, the third question: what will happen if, let's suppose, this is a Faraday cage? We are assuming this is a Faraday cage. This is the front view, and this was a side view, and we are assuming this is the front view. So there is an aperture inside, aperture at at the surface of the Faraday cage. The aperture in the shield can allow external field to penetrate the enclosure, leading to partial or complete loss of shielding effectiveness. The extent of leakage depends on the size of the aperture related to wavelength of electromagnetic wave being shielded. At higher frequencies, such as radio waves or microwave, the impact of aperture becomes more significant. If the size of aperture is comparable to the wavelength of incident radiation, the waves may be able to pass through the aperture, reducing the shielding effectiveness. Aperture can create a resonant effect, which enhance the transmission of specific frequency through the shield. When aperture size matches certain fraction of the wavelength, the resonance occur, allowing more energy to pass through opening. And the edges of aperture can also affect the shield's performance. The sharp edges can concentrate electric field, resulting in increased radiation leakage. Smoothing or curving the edges can help mitigate this problem. So this position of aperture on the shield and overall size of the shielded enclosure can also influence the shielding effectiveness. Placing aperture near the corner or the edges can result higher radiation leakage compared to the center. You know, when there are multiple apertures, each with different size, shapes, or orientation, the shielding effectiveness become more complex. The overall shielding performance may vary across different frequencies, and specific frequencies bands may be more susceptible to leakage. What is the impact of aperture? Small aperture, if the pressure is significantly smaller than the wavelength of the incident wave, Faraday cage can still provide some level of shielding in case of electromagnetic wave passing through the aperture will experience a higher degree of reflection or absorption due to conductive nature of the cage material. In the case of larger aperture, as the size of aperture approaches or becomes comparable to wavelength of the incident wave, the shielding effectiveness decreases dramatically at certain frequencies known as resonance frequency. The aperture can become a resonance structure, effectively act as antenna. When an aperture become resonant, it enhances the transmission of electromagnetic waves rather than blocking them. The electromagnetic energy can penetrate the Faraday cage through the aperture and re-radiate into the uh, interior, defeating the purpose of shielding.